So, today's topic is going to be matrix equations for vibrations. So, um, we're gonna we're gonna write this out. So this is somewhat the first step that you need for multi-degree of freedom vibrations. So we're not going to get too deep into the actual solving of these equations. This is just going to be the setup so that you can understand how that works. So just to give you some background, if we had a very simple 1 degree of freedom system, then it may look a little bit like this, where we have a wall with a spring, and then we have a mass, some mass m, and then we have another spring over here, um, and then so this is a spring with spring constant k1, and this is a spring with spring constant k2. Um, I won't necessarily get into actually solving this system because it's fairly simple, similar to solving the second degree system, which is more general. So I just wanted to give you an idea that this is what we're thinking of when we say maybe a 1 degree of freedom system is this single mass on two springs, and all it can do is move back and forth. So that is the general idea. So let me get rid of this, and we're going to show you what a little bit more complex of a system looks like. Yeah, I'll just drag it like that, and then we'll fill it in. There we go. So now the more complex version of this, and sorry that there's a weird rectangle there. The more complex version of this is with two masses. So with the original system, it's pretty intuitive that if you pull the mass to one direction, then it will recoil in the opposite direction until the spring builds up enough force to push it back in the original direction, and it will oscillate from then on. So this is going to be M1, and this is going to be M2. But it's a little bit harder to see what is exactly going to happen with the 2 degree of freedom system, just because there's a couple different starting configurations that you can come with. But as I mentioned, we're not going to get too deep into the actual solving. This is just to show you how to set up the actual matrix equation to make your life a little bit easier. So this is the general case that we have for a 2 degree of system of this configuration. So we have some arbitrary mass 1 and some arbitrary mass 2. They're not necessarily equal, so they could be, but they're not necessarily equal. So we don't know which one is larger than the other. So then M1 is going to be displaced some value x1, and M2 is going to be displaced some value x2. So this is the distance that it is moved from this equilibrium state. So this equilibrium state is where all three of the springs are not necessarily completely uncompressed, but they are equaling out each other in forces. So this M1, without being disturbed, just wants to stay where it is, and M2 is the same. It wants to stay where it is. But if we do disturb these, then we're going to see some sort of oscillation. So this is a fairly simple case because we don't have any dampers. We just have our little springs here. So this is an ideal situation, and the motion will continue on forever once we displace it initially. But we need to set this up in a way that we can handle the system similar to how we handle a normal 1 degree of freedom system. And the way that we do this is similar to how you would normally start a 1 degree of freedom system to set up the differential equation. What you can do is you can start by doing the free body diagram of one of these masses. But before we do that, we need to make a little bit of an assumption. So I'll explain more on this, but we're going to just assume to start out that x1 is actually greater than x2, and both of them are greater than 0. So the reason that both of them are greater than 0 is, as I said, this is an equilibrium state, So if both of them were 0, we wouldn't see any motion, and that's not very exciting. We want to know what happens when we do excite these masses into some sort of motion. And for the other assumption that x1 is greater than x2, you'll find out that this assumption doesn't necessarily matter. It more matters that we do make an assumption. So you could make an assumption that x2 is greater than x1, and you would get the exact same results in theory. There just would be a couple situations where there would be negative signs because of how you chose the direction of things. But you'll kind of see that, and I'll point it out as we get there. So we're going to start with the free body diagram of this M1. So we're going to go FBD of M1. Oh, that's MM apparently, of M1. And so we're just going to kind of lop this off here, and we're going to see what kind of forces are acting upon this mass. So if we redraw M1 down here, this is M1, then we can see that there is a force coming from K1, this spring 2. There's a force coming from spring 1, and there's also this acceleration due to the fact that we have this displacement. So, but the acceleration itself is something we're kind of trying to figure out. So we're assuming that there is some motion. So what we're going to do is first we'll look at the forces being applied by the spring. And the force that's being applied by the spring, if you remember that springs apply a force that is equal to our kx, just k times the displacement. And we have to look at the direction of things. So since we've chosen this right direction as positive, we're going to try and be consistent with that. So if we look at our assumption for x1 and x2, we can look at which springs are in tension and which springs are in compression. So the springs that are interacting with M1 are spring 1 and spring 2. And so spring 1 is attached to the wall and M1. And if we're moving M1 to the right, then that will tell you that that spring 1 is actually in tension. So a spring in tension wants to pull back to its equilibrium point. So we're actually going to get a force in this direction that is equal to K1 times X1. Similarly, if we look at the spring 2 is, as we saw from our assumption, currently in compression because x1 is greater than x2. So x1 has moved further to the right than x2, or m1 has moved further to the right than m2 has, meaning that the distance between the two of them has decreased, making spring 2 be in compression. So if spring 2 is in compression, if we have a spring in compression, it wants to expand, so it is actually going to push back. And then, so this will be K2 times the distance that the length of the spring has changed. So the way that we find that out is actually it's that difference between x1 and x2. So since x1 is going to be going further, then we're going to subtract x2, and that is our current forces upon this. But as I said, there is also an acceleration associated with this. So we have deemed the right direction as positive, so we are going to continue that trend and say there is some, let me draw this on the bottom actually so that it's a little less cluttered. There is some acceleration x2, and that acceleration is going to be multiplied by our m1, because as you remember, F equals ma, good old Newton. So that is our free body diagram for m1. So we can write an equation for m1, for what is happening to m1, by our good old Newton's formula of the sum of all the forces is equal to ma. So let me just ignore that for now. This is more correct. So the sum of all the forces, we're only looking in one dimension, this linear translation. So all the forces along that linear axis will equal the acceleration times the mass that we are currently moving. So if we expand this out, we can look at the actual formula that this is talking about. So our first equation is going to be our m1 times x double dot, which is the acceleration, is equal to these forces. So if right is the positive direction, then we need to keep that in mind. So what we're going to say is that this is a negative k1 x1. Let me make sure that there aren't any questions in the chat. Nope. And then we have a negative k2 times x1 minus x2. All right. So this is actually our first equation, but as I mentioned, this is a 2-degree of freedom system, so we're going to have two different equations. So what I'm going to do is I'm going to copy this. So maybe we can just expand this a little bit over to the side so that we still have all of our information, but we can actually start our next portion of the free body diagram. So if we draw out our M2, so now we're looking at, we're going to draw this in green so it stands out. We're looking here. Then we can draw out our free body diagram. So we have M2. I'm going to make that a little bit more obvious. M2. And then we have to do the same thing we did before. So as I mentioned before, spring 2 is currently in compression. So this is going to be pushing on M2 because it wants to expand. So that force that's going to be applied to M2 from spring 2 is going to be our same force, equal and opposite reaction, with the spring being over here pushing on M1. That's going to be k2 x1 minus x2. And then our spring 3 is also applying a force to our mass 2. So we can see that it is between M2 and the wall here. So and since M2 is moving to the right, it is also in compression. So we are going to see that there is a force being applied in this direction to our M2 that is equal to K3 times X2. So this is our free body diagram for, this is our free body diagram of M2. So we can write out the next equation. So I'm going to write it here and try to be relatively small. In the same manner, so we have to also consider that there is, this is x bar 1. That's important. So we need to denote that because both masses will receive some sort of acceleration. So we're going to also assume that there is an acceleration in the positive direction that is equal to there's a force due to acceleration that is equal to m2 times our x double dot 2. So we can write out our equation as m2 is equal to, m2 x double dot 2 is equal to our different forces here. So if we have the positive direction in the right direction, then we can see that the K2, this first force is actually going to be positive. So K2 x1 minus x2. And then we have our second force here from spring 3 that will actually be in the negative direction. So minus our K3 x2. So here are our two equations, but it's a little bit more complex to deal with this as two different equations. You can do this. It's not too much more complicated when you're only working with a 2 degree of freedom system. But we want something that's going to be a rigorous method for handling large amounts of masses at a time. Because if you think of anything, you can simulate it as a certain amount of masses connected with springs due to the fact that there's some elasticity, and so it's beneficial for us to have a method for handling a lot of different degrees of freedom. So we want to generalize this while we're still in a simple problem with 2 degrees of freedom. So what you do is you actually want to rearrange these equations a little bit. So we're going to try to get them all in the form of blah blah is equal to 0. So what we're going to do is we're going to move all of this stuff over here over to the other side. But I'm going to do that with the first equation first, just to keep 1 first and then 2 second. So we're going to, I'm going to zoom out a little bit. We're going to say that this is m1 x double dot 1 plus k1. So what we want to do is we also want to collect our terms. So if you look at which ones are variables, we have our variables as x1 double dot, our x1s, and our x2s. So we want to collect all of these, and we'll try to keep them in order. So if they're an x1, then it will also be x. Sorry, if it's an x1, then we're going to do that first, and then if it's an x2, we'll put that second. So we have our m1 x double dot 1 plus our then we're going to have this is going to be k1 plus k2, because you'll remember that these are moving to the other side, so the negatives go away, and that's going to be times our x1. And then since this negative cancels with this negative, we have a positive x2, but then we're moving it to the other side. So now that's going to be negative k2 x2. And that's going to be equal to 0. So if we do the same to this other equation, we can get m2 x double dot 2 plus, so we want to look at all of the x1s. So we're going to have an x1 that is times k2, but that is going to be that's actually going to be positive. When we move it over, it'll be negative, so we want to keep that true. So we're going to say minus our k2 x1, and then we will say plus k2 plus k3 times our x2 is equal to 0. So now we have a format where we have all of the terms kind of lined up, but we want to translate this into a matrix. So what I'm going to do is I'm going to actually expand downwards a little bit, and we're going to write the matrix version of this under these two equations here. I'm not sure where this dot came from, but it is no more. So what we want to do is we want to collect these terms into individual matrices so that we can get something that looks like the original 1 degree of freedom system. And so if you think of a 1 degree of freedom system with only springs and no dampers, then you'll know that that is in the form mx double dot plus our kx is equal to 0. That is our normal form, and so we want to create something that looks like this, and the way that we do that is by putting each of the individual terms into their respective matrices. So if we look at the masses and the acceleration, we can see that in this first equation we have a m1, and we have so the things that are multiplied by x1 double dot are m1. The things that are multiplied by x double dot 2 are nothing, so we're going to put a 0 here. And then we'll look at the same thing in the second equation. So there's nothing multiplied by x1 double dot, and m2 is multiplied by x2 double dot. So these are going to be multiplied by our x1 double dot and our x2 double dot. And so you can see already that this is exactly the same thing that we just mentioned, because if we multiply these out, you'll know that in matrix vector multiplication, the columns of the vector are multiplied by the rows of the matrices. So if we multiply these back out, we will see that x1 is multiplied by m1 and x2 is multiplied by 0. So that's what we get for the first equation, and the same for the second equation. x1 is multiplied by 0 and x2 is multiplied by m2. So then we can do the same for the spring constants. So if we look at what is multiplied by our x1 in equation 1, then that is k1 plus k2. And if we look at what is multiplied by our x2, that is actually a negative k2. Right? So then in our second equation, we can do the same thing, and we can see that x1 is multiplied by negative k2, and our x2 is multiplied by k2 plus k3. So that is x1 and x2 in the vector form. So I need to expand this a little bit more. Right, that should be enough, but I'll keep going a little bit more. There we go. So if we scroll down here, then we can see that our new equation is equal to some vector 0, 0. So if we were to multiply these back out, we can decompose this back into the original two equations. But there's something beautiful about this vector matrice notation that allows us to treat it as if it were a 1 degree of freedom system, and just apply those rules all the way to as many degrees of freedom we want, with a little bit of change here and there. So the reason that we can do this is because we have this M matrix that is dealing with our masses. We have this acceleration matrix plus this K spring constant matrix multiplied by our displacements that is equal to the 0 matrix. The 0 vector. So so these are vectors and these are matrices. And so that is how you apply matrix form for the 2 degree of freedom system. And with 3 degree of freedom system, you will get a similar idea. There will just be a 3 by 3 matrix with a 3 by 1 vector, and a 3 by 3 matrix with a 3 by 1 vector. Now, one thing that I will point out that's just an interesting idea is that you should get a symmetric matrix across the major diagonal. So in this case, we have negative k2 here in the 0, 1 position, and then we have our negative k2 over here in the 1, 1, 0 position. So you can see that that does apply. If you move this up to a 3 by 3 dimension matrix, it should still continue that pattern. And that's a very nice aspect to these equations that helps you out along the way when you have to do something like the determinant later on. And it just kind of simplifies things, that this is just kind of the natural way that things play out. So that's pretty much all I have to say on how to apply the matrix form to a multi-degree of freedom system. I can actually expand on this further in the future if you guys are interested in learning a little bit more about how to actually apply the math to solve these equations. But that's something that I want to save in case people actually are interested in that. So if you are interested in that, please leave a comment below, and I will make sure to do my studying up so that I can do justice to that topic. So that is everything I'm going to say for this specific topic, and we're going to move on to the random drawing.